Welcome to the office. Let's take a look at spheres, right? Circles we're aware of in two-dimensional systems, so we want to take a look at spheres here in our three-dimensional coordinate systems. All right. So before we can do as this exercise asks, find the center and radius of the sphere with this given equation, we have to recognize what the equation should look like in order for us to identify those characteristics of the center and radius. So what we want to do is we want to recognize a sphere is a collection of points course, that makes sense. We'll call them X, Y, Z, which are a constant distance. What is that constant distance? We call it R, constant distance R, the radius from a fixed point, which we will call X naught, Y naught, Z naught, which of course is the center of the sphere. So in a two-dimensional system, if we had a circle, we would say, all right, well, it's from the center, everything is a fixed distance. R, that gives us the points on the circle. We also know, maybe we're familiar with a similar development there, that the equation of a circle is given by x minus x naught squared plus y minus y naught squared is equal to r squared, right? That's a familiar equation for a circle. So here, if we recognize this definition of a sphere, points equidistant from a center, right, from a fixed point, then what we would get is we would get, using the distance formula, we have that the distance between the points, so x minus x naught squared plus y minus y naught squared plus z minus z naught squared, right? That is the formula for distance. This is equal to r. So just using the definition that we wrote down here, we get this equation immediately. But that's not typically how it's given, much like this here. For the equation of a circle, we would square both sides to obtain x minus x naught squared plus y minus y naught squared plus z minus z naught squared is equal to r squared. And this is the typical equation used for a sphere. All right, so now we have the equation of a sphere, and what we want to do is we want to compare the given equation to this equation so we can identify the center, x naught, y naught, z naught, and the radius r. All right, if we wanted to do that, we're going to have to notice that we need to complete the square on our variables, right? We have an x squared, we have a minus 2x, we have y squared, no other y's, z squared, and a 6z. So we want to recognize that we need to bring these terms back together and factor them appropriately. That is, complete the square to have this form of x minus x naught squared. So I'm going to take my equation, x squared plus y squared plus z squared minus 2x plus 6z minus 39 is equal to 0. And I'm going to go ahead and start manipulating that equation. I'm going to group together my x terms. So I'm going to have x squared minus 2x. Group together my y terms, so plus y squared. There are no other y terms. Maybe you want to recognize that there are 0 y's. We'll do that in a moment if you don't hear anyway. And then I have z squared plus 6z. I'm going to go ahead and add 39 to both sides because I know I need that non-zero number on the right. Now what I want to do is I want to complete the square here, here, and here. If I want to complete the square, I need to add a term. And what do I mean by complete the square? Well, just as a quick reminder, if I have, let's call it x minus b squared, right? This is what I would like to have. I'd like to have x minus something, y minus something, z minus something. I should know that this expands as x squared minus 2bx plus b squared. So I want to write them all in this way. All right. So if I want to write them all in that way, I want to recognize that I have x squared minus 2bx. So I need a minus 2 times something times x, right? 2 times 1 gives us the 2 that's there. And then I'm going to add b squared. And for y here, well, I suppose let's comment on here, right? This is the b value to bx, to bx. I'm going to add b squared, so add 1 squared. Then I have y squared. I'd like it to be written as minus, but minus 0 is the same as plus 0, so minus 2 times 0 y plus something, right? So y squared minus 2by. So add the b value squared. Excellent. And z squared. Now I'd like to have it be minus. So I'm going to write this as minus 2 times a negative 3 times z. 2 times a negative 3 gives me a negative 6. When I subtract the negative 6, I get that positive 6. And of course, I could look at the expansion of x plus b squared as well, but the goal is to write it as x minus, y minus, and z minus. So that's why I'm focusing on that. And then I need to add something to actually have the square completed, because I already had this thing. So I need to add this thing squared. And this is equal to 39 plus the 3 things that I added on the left-hand side. So 1 squared is 1, 0 squared is 0, negative 3 squared is 9. So I've completed the square, right? Completed the square, completed the square, completed the square. So I have x minus 1 squared plus y minus 0 squared plus z minus a negative 3 squared, right? That was my b value, my b value, my b value. X minus b, y minus b, z minus b. 39 plus 1 is 40, 40 plus 9 is 49. And so we can write, of course, 49 as 7 squared. So we get x minus 1 squared plus y minus 0 squared plus z minus a negative 3 squared is equal to 7 squared. This side, so this is the equation of the sphere centered at x, y, z, so 1, 0, negative 3, with radius 7. Easy enough. So this is the work that supports that response, of course. And that's all that we have for this video. Join me back again in the office for some more examples in our 3-dimensional coordinate system. See you soon.